quick walkthrough of our MLOps assignment 2. In this video, I'll demonstrate an end-to-end pipeline for cats and dogs binary image classification use case, covering data versioning, model training, experiment tracking, continuous deployment, CI/CD pipeline, and monitoring. I'll briefly highlight the key files and show how everything fits together in the entire project structure. The repository is structured to support the full MLOps lifecycle, including pre-processing, training, testing, deployment, and monitoring. The major components includes DVC for data versioning, MLflow for experiment tracking, Flask for inference, Docker and Docker Compose for deployment, GitHub Actions for CI/CD pipeline, and Prometheus and Grafana for monitoring. Starting with data and code versioning, all source code is tracked using Git. The dataset is organized into raw and preprocessed. The DVC configuration file is included to version large datasets and preprocess outputs without committing them directly to Git. This ensures reproducibility across machines and experiments. Preprocessing is implemented in preprocess.py. Images are resized to 224 cross 224 cross 3 as required for the standard CNNs. The dataset is split into 80% for training, 10% for validation, and 10% for testing, which is exactly as specified in the assignment requirement. Basic transformation and augmentation are applied to improve the generalization and ensure consistency across input formatting. Now we come to model training and experiment tracking. Model training happens in the train.py. A baseline CNN model for binary classification is trained. All experiments are tracked using MLflow, where I log parameters, training matrices, and artifacts. MLrun directory shows the recording runs, including parameters like learning rates, epochs, and model artifacts, such as train model and evaluation output. After training the model is serialized as and saved as model.pth, fulfilling the requirement for a standard model format. The same model is also stored as MLflow artifact, allowing it to reload it across environments. All dependencies are pinned in the requirement.txt to ensure reproducibility. The inference service is containerized using a Docker file, making the model portable and deployable across environment. The image can be built and tested locally using Docker. You see the Docker containers here. Now we go to CI pipeline and testing using GitHub Actions. So we go to GitHub. You can see the GitHub Actions where we are putting, if you're pushing any code, it is in triggering the CI/CD pipeline where from various stages like linting, testing, build, deploy, and notify. Continuous integration unit tests are written using PyTest. This includes tests for data preprocessing, model inference utilities, and GitHub Actions workflow is configured to automatically install dependencies, run test, and build, and the Docker image on every push or merge request. Now we go to deployment and smoke test using Docker Compose and Docker.yaml. For deployment, the project supports the Docker Compose, which is used as a deployment target. The Docker Compose.yaml files defines the inference service and related components. We can run a simple smoke test to see to validate the deployment calling by calling the health endpoint and performing a simple prediction. Now you see the smoke test is running fine. If the check fails, the pipeline is designed to fail as well. Now we'll go to the model packaging where we have packaged the model as model.pth uh, as a REST API defined in app.py. This exposes two endpoints, a health check endpoint for service validation and prediction endpoint that accepts an image and returns the predicted class and confidence score. Now we're going to see that. So we go to Docker, and here you see uh, we can check the health monitoring. So the service is up. Now we go to the prediction service. Here we can see the health check. Now you see the service is up, right? And the status code of service is 200, which is says that service is running. We're going to predict a sample use case. We're going to upload the file. I have an image of a cat downloaded in my folder. I'm going to browse and upload that. The image of the cat, if you look at, is not very clear. It's a side image, and it's uh, not very clear, but still the model is performing better, and it shows a good output. If we execute, now you can see the prediction. It is a cat with a 94% confidence score. So it accepts the image and returns a predicted class and the confidence score. Now finally, we go to the basic monitoring and logging using Prometheus and Grafana. So here you can see the Prometheus is running. I can do a health check, says the service is up. Now we can go to Grafana. Gives my dashboard. Here you see the prediction request count, the predicted class, the confidence score, average latency. So everything is shown up as a dashboard on the Grafana for the monitoring. Now, if you want to reproduce this locally, you can follow the README, which gives the reproducible steps for you to execute this locally. Like you can clone the project, and you can run this command to install the dependencies, and then you can run these commands in serial, or maybe you can run this command directly, and then you train the model, and then you can build the Docker for monitoring, Prometheus and Grafana. Okay, so here how we saw that how this service is running, predicting the class, monitoring is happening. The basic monitoring and logging are implemented using Prometheus and Grafana, and configured into the monitoring folder. The service tracks the request count, latency matrices. Dashboards are configured to visualize the system and model behavior post deployment. So to summarize, this project demonstrated a complete end-to-end MLOps pipeline from data versioning and experiment tracking to continuous deployment using CI/CD automation and monitoring. The entire stack can be run locally using Docker, and predictions can be tested via REST API. Thank you.